Then, so it's my great pleasure to introduce Sanjeevi Krishnan from Ohio State University, who will be speaking to us on homological programming.
Okay. So please interrupt me. This lack of feedback will throw me a little bit. So what I want to talk about today is kind of a motion for a subject that doesn't really exist, something that my collaborator Rob Bryce calls homological programming, some generalization of homological algebra. Oh, wait. The theme of this talk is that there's this analogy between dynamics and algebraic topology in some sense. So the groups are to dynamics as groups are to topology. So anywhere in algebraic topology, you use groups to describe spaces or vice versa. In a similar manner, you should be able to use semigroups to describe dynamics in some general sense or vice versa. Okay. In kind of a recent work of mine and Rob Bryce. And this work is about sensor networks. And some networks have all sorts of interesting topological questions that you could ask them. So those questions you can ask that's particularly amenable to algebraic topology is coverage problem. So if I do a bunch of sensors and I throw them on the plane, and let's say they have some convex region that they sense by these kind of different colored regions, one question you can ask is there some sort of coverage gap? So to make sense of this question, we have some sort of fence describing the outer region, and we will say inside, do my sensors completely cover what's going on? So example where we have a coverage gap is given on the left side, and one won't have a coverage gap is given on the right side here. So this can be tautological or not, depending on what kind of information you have about the sensing regions. So if you know them as subsets of R2, this question is almost tautological. I'm just asking, is the complement of the region inside some sort of Jordan curve describing a fence? Is the complement of the coverage region inside that region, is that empty or non-empty? Okay, that's not a very interesting question. What makes this quite interesting is, what if I only know my coverage region, the sum total of all those colored regions, and the fence region as an intrinsic pair of spaces? Or even, what if I only know them as a pair of spaces up to homotopy equivalence? Can I answer this question? Simpler, let's hack the problem a little bit. Let's get rid of the fenced off region, and let's just, possibly add in some super sensors. So that question really becomes, given region C in the plane, determine if the complement in R2 is empty or not, just by looking at the intrinsic topology of C. So this was answered other questions by Bryce and Vin De Silva in a paper where they show that, hey, you can determine if there are coverage gaps just by computing an appropriate homology group. So in this case, we're looking at the second Borel-Moore homology of the coverage region. So this is a translation of what they've done. So what a Borel-Moore homology is, it's just like ordinary homology, except that instead of having chains, finite chains, you have locally finite chains. So possibly infinite chains that locally are finite. Allow my homology classes to be represented by these more general chains. I call it Borel-Moore homology, not just literature, and just compute straight out the Borel-Moore homology of the coverage region, and it's trivial. That's telling you, hey, some sort of coverage gap. And initially, what's going on is a gender in Borel-Moore homology is really giving you a way of tiling C. Is really telling you that C has a way of tiling the plane. So there's something non-trivial going on there, then in fact you've covered the entire plane somehow. So this is kind of one criteria among many insights about sensor networks that Bryce and Vin De Silva have shown. There's some technical hypothesis we have to make our coverage region. We have to assume it's something nice. So here it's a closed sub-CW complex, and its complement has compact closure. Nice because here the Borel-Moore homology only depends on the topology of C. Another way of completely characterizing sensor coverage, and this is given by Alexander duality. So Alexander duality it's really essentially a composite of a boundary homomorphism and Poincare duality. So it's really a duality between the cohomology of nice spaces and the homology of their complement in Rn. So there's a little bit of a typo here. I should have, instead of n, I should really have 2, but this one is given as follows. So I start with some open subset of R2, so it's open manifold, and the cohomology of that is really isomorphic to the homology of the complement. Technical hypotheses. Okay, so duality. If our coverage region were in fact an open subset, or let's say if we look at the topological interior of a really nice coverage region, we can use the existence or non-existence of coverage gaps. That is, we can deduce the triviality or non-triviality of H lower 0 of the complement, computing H upper 1. Okay, so another completely intrinsic way of answering the question, do my sensors completely cover the plane? And this is something even slightly better because it very plainly only depends on the homotopy type of the coverage region. Okay, now myself, well, let's perturb this problem just a bit. Suppose my sensors aren't just static, so we move around just a little bit. And maybe there's some noise, maybe sensors once in a while can flicker in and out of existence. In this problem, it's no longer interesting to ask, do my sensors always cover the plane? But it's interesting to ask, is it principle for some suddenly fast and smart data to move in such a way so as to avoid my sensors at all times? Okay, so give a mathematical formulation to this problem. Instead of having a plane as my ambient space, let's take a space-time. Okay, so this is a very silly space-time. I'm just looking at R2 cross R. Okay, or in Falutin terms, I'm looking at vector bundle over R with an R2. Okay, coverage region is a subset of this space-time. It's a subspace of my vector bundle. And the question is, if I look at the complement of my region in my space-time, I want to ask, does that complement as a space parameterized over the timeline that admit a section? Okay, telling me whether I have an evader that can intelligently move about in such a way so as to avoid sensors at all times. So here is an example of the complemented region, E minus C, in the top, projecting down to the real number line. And this is an example where evasion is possible because that projection down to the real number line admits a section. Back up. Okay. Non-example. Here's an example where my complemented region, E minus C, does not admit a section. See very clearly there's a point of discontinuity where sensors completely cover the plane at some time, and therefore evasion is impossible. So a necessary condition for evasion is that no point in time has complete coverage. We see here, okay, if we check at each point in time, aha, at some point, I apply either Vinda Silva and Rob Grice's condition, or I can apply Alexander duality and include in that achronal slice that evasion is impossible. Now, to perturb that example just a bit, I also example where evasion is impossible. So here again is my evasion space. There's some gap in coverage. It's just that those gaps in coverage are not continuously related to one another. So I don't get a section. Still not really fatal, because I kind of generalize my notion of an achronal slice. I get these kind of bendy achronal slices. And the notion of Grigova is that, hey, we still get a necessary condition for evasion. It's just that none of these bendy achronal slices are completely covered by sensors. In general, and it gives us a little bit of a stronger condition for evasion, but good enough, shown by the following example. So my evasion space, if at no point in time, not even one of these bendy achronal slices, do I have complete coverage by sensors. Yet at the same time, evasion is impossible here. I don't have a section, and it's because time travel is impossible, right? I can't follow along and then go backwards in time, loop around, and continue all the way. That would not be a section to this space parameterized over the real number line. You think to yourself, okay, But what do I really want? I really want to get an evasion path. I really want a coherent choice of points in my evasion space at each point in time, and I want them continuously chosen with one another. So I'm going to say to myself, if I want to algebraicize this, I want some sort of coherent choices of generators in H lower 0 of the fibers of my space here. Okay, if I can coherently choose generators for my H lower 0, then maybe that really corresponds to, that's good enough to tell me there's an evasion path. Okay, but that's even, and there's a name for a coherent choice of generators in H lower 0 for sufficiently nice space that's parameterized over the real number line. This is called zigzag persistent homology. And an observation of Henry Adams and Gunnar Carlson is, hey, there are some examples such as this one, where you compute the zigzag persistent homology, you'll see that you have a coherent choice of generators in H lower 0 for the fibers for each point in time, get a persistent barcode in degree 0, yet at the same time evasion is impossible in this example. So something as refined as zigzag persistent homology still isn't enough to give you a sufficient condition, only a necessary condition. Okay, so we have three topological conditions that are necessary but not sufficient for evasion, given by Borel-Moore homology, given ordinary cohomology, and given by zigzag persistent homology. So you might say that algebraic homology is very well suited for static problems where things are not dynamic, like sensors that are fixed on the plane, but they introduce some sort of dynamical variant of a problem. Algebraic topology doesn't completely answer the question. Okay, and this is necessarily so, and by this following last example. Okay, we want to think of new ideas, and one thing that Hans and Gunnar Carlson show that if you really, in an essential way, need to take into account more information from your coverage region. So we have more refined information in our coverage region and computable invariant on the coverage region. So we'll have positive homology and positive cohomology here. Positive homology and positive cohomology. Well, real homology are vector spaces. Think about how maybe some positive cones in these vector spaces give us information about the underlying space. Okay, by a cone, I mean a convex cone in a vector space. So something like a positive orient in R and in R3, or you can also look at ice cream cones. They don't have to be polyhedral. They can be smooth, like Lorentzian future cones, actual cones. Of cones. So, an example of defining a positive cone on a homology vector space. Well, a simple example is in zero homology. So I can think of zero homology, ordinary zero homology, as being combinations of path components, right? That vector space, I can define positive cone as just being generated by the path components. So non-negative linear combinations of path components. So this is somewhat of a silly example, but really, if you think about it, something is going on. If you looked at ordinary homology, you can recover information about path components. What you can recover is that you can choose a set of generators, but there's no guarantee that those generators actually represent path components, are represented by path components. They might be, for example, linear combinations of path components. And if you look at this positive cone, you can actually recover the path components naturally, the generating rays of the positive cone. Okay, so in terms, the homology is a stable invariant on the space. Ignore certain unstable information about X, but the cone actually recovers that unstable information. It's natural to ask, I have cones in zero homology, Alexander duality. Following the duality, what's Alexander dual to this cone? And we can cut a cone in cohomology group. I look at a manifold, so faced with enough structure here, an oriented manifold with break.
Sorry, can I interrupt you for a second?
Yeah.
Can you explain again the what the positive cone on the zero homology is?
Yeah.
How
So
should we be thinking of that? Or what's an example?
so an example is if I give you two disconnected points, right? The homology is R2. All right. So and the positive cone is just very only going to be 2 R plus of the negative reals or the positive reals. If I do.
The cone on the ground field is that?
The cone is a subset of the vector space of H0x. So X is just 2 copies of R. The cone is going to be 2 copies of the positive real.
As the real numbers here, you're taking homology with real coefficients?
Yeah, real homology.
Okay.
Yeah, sorry about that. Thanks.
All right.
And it's not technically 2 copies of real, but rather all non-negative linear combinations of path components.
Okay.
Okay, I'm still not clear on this. It's you're claiming that by working this positive cone instead, we get the bond components and not some sort of question. And I have a hard time seeing, given that you have this vector space sitting, what the expect definition would be, or this guarantee can actually be fulfilled.
Last thing one more time.
How can we be sure that the generators for the positivities actually corresponding directly to path components? It's in no way obvious to me.
You're right. You can't, but they're most unique. Unlike vector spaces, these cones have this particular choice of the cone has almost unique choice of generators. It's unique in the sense that it's up to scalar multiplication by non-negative reals. Right? Are going to be either the two represented by the 2 path components or some non-negative scale of either of these path components.
Something that sits inside the vector space of H0x, right?
Yes.
Is there a right procedure to go all the way from chain modules to the positive cone directly, or is it something you pull out of the vector space?
No, vector space already ignores lecture, right? So we're secretly thinking about H lower 0 as being constructed in this very concrete way as linear combos of path components. And then we're defining the positive cone to be this, non-negative linear combos of path components.
So basically, topological.
Yeah.
I'm waiting for the algebra. I'll let you go on.
Yeah. If you have H lower 0 of X, if that's all you can see, then you can't recover anything. Extra structure to H lower 0 of X that refers enough of the information about X to recover the path components. Okay. 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 It's not meant to be very deep, but that's just kind of laying the motivation for why we're defining positive cones here. Okay, so what's Alexander Dual to this very full-minded definition of a positive cone? Well, you have to posit that there's enough structure on your space. So we're going to look at oriented n-manifolds with boundary, such that the boundary is compact. And is a certain pullback, but in words, the cone that we want to define on the n-1st cohomology of this manifold is just all n-1 cohomology classes, which, when restricted to the boundary, really kind of given in the same direction as the orientations on the boundaries. So a very simple example is illustrated here. If in the gray region I have my manifold, some manifold with boundaries sitting inside R2, I have the positive 1 cohomology classes are such that when I restrict to the boundary, which is a circle, I get something that's moving along in the direction of the orientation, induced from the orientation of the manifold. Okay, and that's your definition of a positive cone. on n minus first real cohomology of the manifold, that definition, we get this positive Alexander duality. So we can say that positive cone in A lower 0 is Alexander dual to this new positive codimension 1 cohomology. Intuitively, what's going on in this example, it has for every one of these positive 1 cohomology classes that's wrapping around the boundary, that corresponds exactly to a path component sitting inside.
Okay. We can see that from the pullback definition, how we get this picture from the pullback.
So in the pullbacks, so that is just literally saying, okay, so we have, it's a sort of, I'm looking at, I have as my right map, so identify the n minus first cohomology of the boundary of the manifold with the zero homology of the boundary of the manifold via Poincare duality. I already defined what a positive cone is for zero homology. Okay, so that's above. So I have a positive cone sitting inside the n minus first cohomology of the boundary. A typo here. On the box, it should be the n minus first cohomology of M, not the boundary of M. But map from n minus first cohomology of M to the n minus first cohomology of the boundary of M, and that lower horizontal map in that diagram. So literally, those classes in n minus first cohomology of M, not three of them, M, which restricted to classes on the boundary of the manifold are positive in some sense. And positive really means in the same direction as the orientation on it.
Okay, thanks.
Given enough technical hypotheses on manifolds with boundary, we get this Alexander duality, degree 0 homology. Okay, that's what we want. We want for the next homological degree, set of cones on 1 homology. So again, it'll be a pullback diagram, but let me explain in words what's going on. So we're doing positive for the homology of a space that's parameterized over the real number line. Okay. So the mission for this is you want to think of the evasion space parameterized over the real number line, and we want to find what positive Moore classes are for that evasion space. So the mission is that the ordinary Borel-Moore homology is going to consisting essentially is describing various paths in the space parameterized over the real number line. Paths that are going horizontal, maybe paths that are completely supported in a fiber. Look at essentially the Borel-Moore classes are kind of going in the direction of time. It's this following pullback diagram, which isn't very illuminating, but kind of intuitively what's going on is in this illustration down below. So they've shown an example of a parameterized space over the real number line. So the illustration is G collaborator Rob Grice. But so you have kind of tube representing P. Okay, the kind of the stride represents a Borel-Moore 1 homology class. So it's kind of around like that. And what we ask is that we say that a Borel-Moore 1 homology class is positive if it interacts positively with every fiber. So in the sense that if I look at every fiber, it should be cutting through that fiber up to homology in the direction. So we have something that's cutting to a fiber from left to right, one piece of the fiber from left to right, but another piece of the fiber from right to left. And that's not allowed in the positive cone. So this would be an example of a Moore 1 homology class that's not positive. And find this in terms of natural maps between homology groups. So in terms of boundomorphisms, you can define what you mean by intersecting positively or negatively. Okay, essentially, a positive homology class is generated by paths that are all going from left to right, that are all following the direction of time. And the useful thing about this positive one homology is the following: is that sufficiently nice space that's priced over the real number line, that space has a section if and only if some variant of this positive one homology, so enough of these positive one homology classes are non-empty. So notice that you have you can talk about committed homology. That's ordinary homology. There's something like compactly supported homology, but this is really Moore homology that's supported on proper spaces over the real number line. So if that kind of my positive cone on Borel-Moore homology is non-empty, that's section. What makes it a little bit weird is there isn't a one-to-one correspondence between in the positive cone of Borel-Moore homology and sense of P, but almost. Questions, please don't end. I know this might confuse the way it's written. Okay, I have this kind of positive cone on Borel first homology that actually detects existence of sections. That's the takeaway here. And so, what's Alexander dual to that? Following Alexander duality, what's the appropriate definition of positive cone in an appropriate degree? So, look at a space parameterized over the real line. The n here is really P of P is really an n manifold, and you want to think of P as a n plus one dimensional space. So we're defining the positive cone on the S first cohomology of an n plus one dimensional space. So this is positive cone on code 2 cohomology, and it's essentially doing is saying that in the n minus first cohomology of P is really positive if, when restricted to every fiber, it's positive in the previous sense. The example that kind of illustrates this definition is given below. So I have my illustration of what P looks like, this winding space, parameters over the real number line. And it's some sort of thing that's almost everywhere a manifold. And if I look at each point in time, I ask myself, well, my P class restricts to something on that fiber, and it restricts further to the boundary. Am I really going in the same direction of the orientation? Notice here that any cohomology class that I define can be winding around all the circles in the same direction. And some have to be winding around in opposite directions, so that combine at the bend to a zero homology class. Okay, so this is of pod cohomology. So the n first cohomology of this n plus one dimensional space P parameters over the real number line. And it gets defined as a pullback diagram. That just means, we're formalizing what we mean by saying it's a certain distinguished subset of n minus one of P. Okay. And then we get positive Alexander duality for these definitions of positive cones in the first homology of E minus C and the positive cone of the cohomology of a coverage region C. So there are technical hypotheses we have to make about our coverage pair now. We have that our coverage region is a closed subset of our space-time. We have to assume that the complement of the coverage region at each point in time is pre-compact. It has compact closure. And we have to assume that our coverage regions are almost everywhere they're manifolds with boundaries to work. A slew of hypotheses were so bad in reality, but we still have to list them. We get this kind of positive variant of Alexander duality.
And so E is the ambient space, and so C is the covered region, and E minus C is the complement, or vice versa. Is that correct?
C is covered region, yeah, and E minus C is the evasion space.
Okay, thanks.
Okay, positive Alexander duality. Given the lemma allowing us to detect existence of sections, we get a criterion for evasion. So, unsuitable technical hypotheses on our coverage pair for ambient space E and our coverage region C, we actually detect whether or not there exists a section that map from E minus C to R, just computing an appropriate positive cone of the region. Okay, that's story. Okay, and this criterion really only depends on intrinsic geometry of C. Its topology and its orientation as something that's almost everywhere a manifold with boundary for all points in time. So, okay, that's great, but how long do we know if this is computable in any way? So, but how you actually calculate this, and this is what actually kind of motivate a putative discipline of homological programming. So,
I want to interrupt really quickly.
Yeah.
I have a question. So I think there's some examples where you have two covered regions that are sort of fiber-wise homotopy equivalent, and the two complements, one is an evasion path, but the other doesn't. So in the theorem, you're using more than just the fiber-wise homotopy type of the covered region. Can you say a little bit more about what you're using?
Yeah. So this positive cone on the n-1st cohomology of C, it depends not only on the homotopy type of C, but all orientation information on C. So you have C as, so go back to the slide here, we have this coverage pair. You have C as a closed subspace of a trivial vector bundle, which is a natural orientation on it. We have to remember the orientation C inherits from E.
I see.
But like your ring structure, right? The ring structure remembers the orientations, right? But all the positive cohomology uses is this orientation information plus homotopy type information of C.
Very cool.
Okay. So let's actually do this in practice. Do a calculation. Well, let's sort of do a calculation. Let's how calculation go. So the main observation is that positive cohomology decomposes a limit, local positive cohomologies. So in kind of the pithiest language we can choose, we can think of cohomology or positive cohomology is really finding a sheaf on the coverage region. So if I have my region C, right, think of it's some sort of stratification on the real number line. I wrote that. Well, let me skip ahead to this here. So look at this yellow region over here, and suppose I stratify it. So I have some vertices and I have edges, but I can really think of positive cohomology, which is contravariant, as really defining a sheaf on this. So over the stars of the vertices, I can look at either cohomology of the appropriate pairwise space, and the interiors of edges, I can look at the positive cohomology region over that interior of an edge, and a sheaf. I get a sheaf of positive cones over the real number line. So then I can say to myself that positive cohomology of the total region over R is really computable just as a limit of these kind of local positive cohomologies, stars of vertices and interiors of edges. This reduces the problem to essentially computing the limit of a sheaf of positive cones and those local positive cohomology cones. So we can put this in a bunch of calculational steps. So if I have coverage region C, I compute the cellular cohomology sheaf, which is just taking stars of vertices and edges compute the cohomology over those regions of the real number line, and then finding the distinct cone sitting inside. So the cellular cohomology subsheaf. It's a positive cones over open stars of vertices and open stars of edges, and letting all that information together, taking the limit or the global sections of that cellular sheaf. Okay, so that example, right, where evasion is impossible, so identification of the real number line, and then open stars of vertices like that one, I compute the positive cohomology. So all that means is compute the ordinary cohomology, and I have to just ask myself, well, which cohomology classes, when restricted to the boundary of the manifold at each time, are winding around in the right direction? I can get a positive cone in the cohomology of the yellow shaded region. Every open star of a vertex or a cell, or a vertex or an edge in the timeline. So like this thing, I can do that for everything. I'm getting a bunch of cones of real vector spaces corresponding to vertices and edges. I get the cellular sheaf, right, of positive cones. Generally, I get them of certain semigroups, cumulative commutative semigroups, and I compute the limit of the cellular sheaf. So what is the limit of this sheaf? It's nothing more than an equalizer between two maps. So what I'm doing is I'm taking my sheaf abstractly, I'm taking product over the product of the values over the vertices, the product of the values over the edges, and then at two restriction maps. And I take the equalizer. If I look at all the things in the first product that map to the same things in the second product, that's global sections of my sheaf. That's my elements in my positive cohomology. Going back to the slide, I just compute the product of my positive cones over my vertices, the product of my positive cones over my edges, and then compute this appropriate equalizer. This limit or equalizer.
So, Sanjeevi, what is too much there?
Oh, yeah. So I didn't really define it, but if we go over here, right? Right? I can think of delta minus as restricting to the edge on the left side of that vertex, and delta plus is restricting to the right side of that vertex.
Okay.
So that's from the value of the positive cone over this vertex to the value of the positive cone over each of those edges. And I can get a parallel edges from the product of over the vertex, the product of values over the edge. Okay. Equalizer of that is really the limit of the sheaf. It's giving me the global sections of my positive cohomology. In homological algebra, if F were really just a sheaf of vector spaces, we can keep this limit by just taking the kernel of the difference. If F is a sheaf of groups or just groups, right? I have to take a kernel of the difference between those two group homomorphisms. But if I'm the next best thing, if I'm a semigroup of a group, then my limit is almost a kernel. It's a kernel of the difference interacted with the first guy. Okay, thinking of it as vector spaces, right? I have delta minus and delta plus are maps between positive cones of vector spaces. So the difference is living inside a vector space. It's really just a linear space, right? Section of my values over vertices is a positive cone, and can compute using linear programming. So a positive cone is described by certain extremal rays, and just by choosing appropriate constraints, I can intersection of a half plane with a positive cone as a problem. I want to say about linear programming. I really don't want to get into details, but if you have any questions, you can ask about that. But the central point is there is a computable way of getting this limit. F is really a sheaf of cancelative commutative semigroups, or especially if they're a sheaf of positive cones in vector spaces. That actually is what's to kind of motivate a generation of homological algebra. Here we have a problem, the pursuit-evasion problem. We can completely answer it just computing an appropriate global section of a sheaf of positive cones. And to compute that, you have to do some sort of linear algebra, or algebra and some linear programming. A combination of the two things really belong in some subject that we might call homological programming. So back to this pursuit-evasion problem. You computed H_1, the positive H_1 of the C, you'd see that the global sections of this sheaf of positive cones is actually empty. No evasion path that's possible at all. Do this, so you'd form a giant matrix, right? Ordinarily, you compute the kernel. How do you compute, of vector spaces? You're going to compute the kernel of a differential map. Here, we have two maps. We can take their form differences, right, and get a matrix here. This is kind of like the formal difference of delta plus and delta minus. And we can look at the kernel, the ordinary kernel. I don't know, it's not. Well, if I were to compute the kernel of this map here, I actually get actually correspond to a generator, a column of this matrix here. Okay. If I the equalizer of that map, if I looked at the column that corresponded to a generator in the kernel of this map, I see that it contains negative terms, so it can't be an element in the equalizer. That's how I know that positive cohomology is empty. If I just kind of switch around this example so that evasion is possible, and I go ahead and actually compute the first positive cohomology, such that it's isomorphic to Z plus, I said that it's really R plus, given the restriction that we have to real coefficients. So it actually has a single generator, and that single generator corresponds to essentially unique way of evading sensors in this example. Okay, so we can form a matrix where the rows correspond to in the cohomology of the overages, and the correspond to generators or vertices, and I get a matrix that corresponds to that differential map. I take the difference between my positive and negative differential maps. In order to just compute the kernel, I would correspond to some sort of combination of the columns. See that linear combination of column vectors that actually consists of three positive entries. So, example over here, if I look at my columns, right. So if I added these columns together, that's inside the kernel of them by this matrix. And notice that if I'm adding these columns together, I'm not subtracting any columns together. So the element really does live inside the positive columns. How you do positive cohomology, which is completely characterizing evasion for real kind of sensor networks. Now is where I care about computing equalizers and co-equalizers, and that's more generally from directed topology. So one thing you can think of is everything we've done so far is about spaces parameterized over the real number line. That's a very special case of a space-time, some notion of space with some time on it. So this parameterization over the real number line really induces flow of time on the space above. But there are examples of spaces that we care about. One example, directed graphs. Or if I care about topological examples, geometrizations of directed graphs. So there's an example where I can just map down to the real number line and get a notion of a global clock that's inducing some time flow above. Yet again, locally, there's some flow of time. Other examples. So if I look at state spaces of very complex processes consisting of more than one thing acting at the same time, I have high-dimensional spaces where there's some notion of time flow on them. again, just merely given by mapping to some real number line. Or abstractly, I can look at abstract things like small categories, right? And classifying space, that really ought to have some notion of time flow on that, encode a one-way directionality of the morphisms in the category. Okay. So an example comes from geometry. I can look at manifolds with distinct cones of vector fields telling me what's the direction of the future. Okay. I have some sort of topological space plus some extra structure. And example of kind of, so then given these kind of spaces, I can talk about a homotopy theory appropriate for these spaces, and it's called directed homotopy theory. And one example of invariance on these directed homotopy, one example of directed homotopy invariance is exactly my evasion path up to homotopy. And of our discussion before is reading a special case of directed homotopy theory. I do combinatorial models of directed spaces, like cubic sets. So these are just ways of gluing cubes together. Orientations on the edges, giving me a notion of time flow on them. Convert all my example directed spaces into cubical sets by an appropriate singular functor. And the next is that once I have cubical sets, I can define homology and cohomology very similarly to how one might define homology and cohomology in the topological setting. So, for example, if in a cubical set just consisting of elements in degree 1 and degree 0, right, this is nothing more than a directed graph, and I can define for you homology and cohomology with coefficients in the natural numbers. I just take n-linear combinations of abstract edges and abstract vertices, the appropriate positive and negative boundary maps, which are intuitively just giving me source and targets of this. And then homology and cohomology is just appropriate equalizers and co-equalizers. So I need to do something like before. I need to compute times the intersection of an equalizer, a kernel with a positive cone, or normalization of a positive cone. More general cubical set, I can see more general things that are called in the literature quasi-parity complexes, which are generalizations of chain complexes that have minus signs anymore, and very abstractly define the nth homology and nth cohomology with coefficients in the natural numbers as appropriate equalizers and co-equalizers of these maps modulo appropriate congruence relations. Finally, we can do a small example. If you look at a space-time Klein bottle, so in sphere with the identifications given a cone, there's a natural notion of time flow going kind of diagonally upward to the right, and compute the homology with natural number coefficients of this space-time Klein bottle. And this weird commutative monoid with two pieces of the natural numbers with weird relation that times one of the generators equals 2 times the other generator. And as we take the group completion of that homology, we actually get the ordinary integer homology of the Klein bottle. Okay, so interesting going on where we can compute this directed homology and directed cohomology in this absolutely simple-minded way, retain the extra kind of dynamical information given by that directed space. So to ask, well, there ought to be some generalization of homological algebra that's for actually computing these invariants. So we have as follows. Instead of having kernels, we're computing equalizers. Instead of kernels, we're computing congruences. And when you're given a linear map, you know, if you want to compute kernels, one way to do it is to do Gauss-Jordan elimination on a matrix. And we're doing some sort of linear programming here. And then ultimately, at the end of the day, we're using this to compute cohomology or homology, either a classical or a directed setting. And you know, the thing I want to pose is, can we continue this dictionary further? Can we really build the kind of insights from homological algebra into the homological programming? With then the fact that this analogy ought to continue in some way. For instance.
So do we have more questions for Sanjeevi?
So Sanjeevi, I'm struggling a little bit with seeing the how all of this translates to algorithms. Do you have implementations? Are these things sitting in software somewhere?
So that would be a great project. I mean, you can just take off-the-shelf linear programming libraries, and we should be able to do this. You know, we should be able to do this. I mean, the tricky thing is, at the end of the day, you have to go through homology. So going back to this, you have the positive cohomology of at least some local areas. You probably do this by computing the ordinary homology and convincing yourself that you know what the cone inside this is. Which of the elements in this homology or cohomology satisfies the criteria of positivity.
Well, Justin mentioned in the chat that this obvious in the case of zero homology, basically by your division by fiat of being generated by components.
Mm-hmm.
Do we have reason to think there are criteria for what it should mean to be positive in the middle dimensions?
No. So, I mean, the kind of definitions here are tailor-made and almost tautological to solve the pursuit-evasion problem. I mean, even though the definition of positive cones in H lower 1, yeah, that's kind of tailor-made to detect sections, but it's still non-trivial to prove that it actually detects sections. You almost have to, definition depends on what you want to detect. And the definition of positive H lower 1 doesn't always necessarily coincide with the definition of directed homology that I give you later right here.
The entire rest of the chain, I can reasonably well see how it would fit together, and it's something I could imagine throwing at a student as a project. I'm really stuck on the positive homology cone bit. I don't see how that's happen algorithmically or algebraically in any sort of generality. So doing it by fiat as connected components, we can just throw graph algorithms at it. But anything beyond that, and I'm stuck.
Okay, I mean, well, your starting point would be actually computing the ordinary cohomology of, say, this local region, right?
Sure.
Sorry?
Sure.
Yeah, and then you'd have to hope that, you have to get some representatives of that cohomology, and you have to at least be able to restrict to the boundary of that thing as a manifold with boundary.
All straightforward. I can see roughly how that could fit in code.
Right, and check that the cohomology class is going in the prescribed direct orientation.
And meaningful in all dimensions and obvious from the manifold structure?
It depends on how given the data. Yeah, I thought too clear about how to implement this, but that's a good question.
All right, I started on thinking about it. I'm happy. Thanks.
Sanjeevi, Bala Krishnamurthy. I had a question about the user programming. So what do you use as the objective function? Are you minimizing or maximizing something?
Yeah, need to. Okay, so technically we need to. Our objective function would be something like. What do we want to say? So R would be like the norm B1. We're assuming we can put norms on these vector spaces.
Mm-hmm.
Yeah, so.
You don't necessarily have to have an objective function every time, but I was just curious if you indeed, or are you just looking for feasible solutions?
Well, no, I just want elements on this intersection because that's infinite. I would say kind of extremal rays. So I mean, there is a way to define an objective function so that this will be kind of the extremal rays of this cone. I'm just not seeing right now.
Okay. norm, okay, Euclidean norm, then it won't be linear, right?
Oh, yeah, you're right. I have to find that constraint.
In the cubical, or if you were to think about simplicial setting, you might go doing it as a one norm, and then you can linearize it.
Yeah. Yeah. Yeah, the key thing is that, okay, you're constrained to be something so that, you know, here this is cheap, but okay, objective functions should be the thing so that the solutions, so you maximize it, you get extremal rays in the next body. And your constraint should be something so that you're looking yourself to just a unique vector in an extremal ray.
Simpler linear programming language, maybe an analogy would be that you want the vertices and not any point in the source, so to speak.
Yeah, exactly.
Okay.
Yeah. So I want to slice this guy by something. Okay, it can't be a sphere, so it can't be the ordinary norm. But yeah, it's linear to get linear norm, you're right. And then that's an objective function. Essentially, you're looking at that cone, you want to slice it by some linear space. That would be look at what that intersection is. That's the objective function, is taking section with linear space. And then the objective function is maximizing the width of these things so that these are at the extreme of convex body.
Okay, thanks.
Yeah.
Sanjeevi for a great talk. Thanks a lot. Thanks, Sanjeevi.
Thank you very much.